Okay, fine. So we continue indeed this morning with the debris disk. You had this talk previously by Debbie on the observation. I'm going to speak about how you can extract information about the debris disk that you see with various kind of observatories. I'm not going to discuss the dynamics of the dust particles, neither the dynamics of the planetesimals themselves. So I refer to the talk of Mark Wyatt later. I think it's tomorrow, to discuss a little bit more about the dynamics. Does not work. Okay. Okay, so what is a debris disk? I guess you know now. It's basically a planetary system, right? So you have planets. Okay. You have planets, but you also have in extrasolar planetary systems, you have small bodies, comets, and asteroids. And obviously, you don't see them directly. But fortunately, they do produce dust, and you see this dust. And the job is actually to infer the population of planetesimals that you don't see directly from the dust that you observe with different observatories. So I divided the debris disk in basically two categories. The cold debris disk that you can see here on these examples. This is a reformulate debris disk. This is a beautiful ring, a narrow ring that is very cold. It's sort of extrasolar analog to the Kuiper belt. And you can also define another category of debris disks, the hot or warm debris disks that you don't see here on this picture, which are very close to a star, which I will only very briefly mention at the very end of my talk if I have some time, but there is a talk by Denis Defrère later on. He will discuss that a little bit more in details. Why do we want to model debris disks? We want to know what are the grain properties of these disks, what is the composition of the dust grains that we see, because they basically reflect the composition of the big guys that we don't see directly. We want to know what is the size distribution, because you want to know if your system is in collisional equilibrium, for instance. You want to know where is the dust located around the star, and if you see some asymmetries, that could be due to the presence of planets. And overall, what you want to know is, what you want to get is a complete census of the constituents of planetary systems, from the tiny dust grains to the very big guys, including Jupiter mass planets, from very close to the star to a very distant location from the star. And you want to use this information to infer the dynamics of your systems. And that would be great if you could do that for many extrasolar planetary systems, but in practice, what you get is usually an SED. That's all. A few photometry points here, which do show that you have an excess due to a cold debris disk, and this is a star, and this is a disk. And most of the debris disks which have been detected have not been specially resolved, and you want to start with an SED to extract some information about the star, the disk that you observe. So let's do that. When you have an SED like that, you can calculate the luminosity of the star, the luminosity in the infrared, the thermal emission of the dust. You make the ratio, it's very small, and that tells you basically that it is optically seen. I mean, this ratio is to the first order, the optical thickness of your disk. So definitively your disk is optically seen. In this example, this is a few 10 to the minus 4 only. That's very convenient, because obviously for the radiative transfer, you don't have to deal with a complex radiative transfer code. The other thing you want to extract from such an SED is the temperature. So you fit a Blackbody to these data points, and you get a temperature. And from the temperature, then you can get a disk radius. How do you do that? That's very simple. You assume that the grains are in thermal equilibrium, which means that the luminosity which is absorbed by a grain is equal to the luminosity which is emitted by the same grain. So you do a little bit of mathematics, that's not too complicated, and you get a distance, which is the distance at which the dust should be located. The bulk of the dust that you see that is producing this emission should be located. And you see that it's very convenient, because it only depends on two parameters, the luminosity of the stars, that in principle you know, and the dust temperature that you obtain by fitting a Blackbody to this SED here. It does not depend anymore on the grain size, which is A here in these equations. So let's see if it works. let's do that. So I collected in this table a few systems which have been specially resolved with different spectral types, different luminosities, and different dust temperatures. And these are the black bodies, radii, which are predicted by the laws that I just showed before. And in the last column will appear the observed location of the dust. So let's do that for reformulate again. This is predicted, the dust is predicted using a Blackbody approach to be at 75 AU. It is observed at 140 AU. Let's do that for HR 4796. This is a sphered image of the disk. It is predicted with a Blackbody approach to be at 30 AU, and it is observed at 70. Sorry for that. Yeah. I try to not forget it here. Let's continue with another one, HD 181327. It's predicted to be at 25 AU. It's observed at 90. So I'm continue like this with another disk observed with Herschel, predicted at 27, observed at 75. Another one, HD 15115, which you might not guess directly on this image, but this is a ring, very inclined ring at 90 AU, so almost 3 times larger than what is predicted by the Blackbody law. And this is the last example here with using this Herschel image of HD 207129. The disk is predicted to be at 35 AU and observed at 160. So what's the problem here? The problem is very simple. Let's have a look again at this flux versus wavelengths plot. If you assume, if you consider black bodies, you consider that basically your grains are emitting and absorbing very efficiently with a unity efficiency, whatever the wavelengths that you consider. But in reality, this is not the case. More real grains do indeed absorb very efficiently at short wavelengths, but at some point, they become less and less efficient to absorb the stellar emission and to emit the stellar emission. And this break, this position and the shape depends strongly on the size of the grains and the composition of the grain and many other parameters. So the bottom line here is that the small grains are very poor emitters at the wavelengths where the disk SED peaks, which is the main problem when you consider black bodies instead of real grains. So as a consequence of that, they absorb as much emission as the black body grains, but they emit less. So the consequence of that is that the temperatures of real grains is larger, usually, than the temperature of equivalent black body grains. So you can change your equations. I'm not going into the details here. Just if you have some time later on, you can actually do the mathematics. And you're reaching the point where you have a distance, the location of the dust, which depends again on the luminosity of the star, which is here the flux, but integrated over the wavelengths. And it depends on this parameter, Q-abs, which is a unitless factor, which describes how efficiently or not efficiently the grains do emit and absorb the light of the star. Okay, so the basic conclusion here is that the Blackbody approach is very convenient definitively because you have very few parameters, but it has so many limitations, and you have to take care of them. The first thing is that you don't have any information on the grain size because the grain size disappears in your equations. The second is that it does predict very poorly the position of your dust, and it's not very good, especially if you want to actually use this constraint to say, okay, there should be dust here, so there should be a planet at some point near here. No, obviously, if you did that exercise using black bodies, you will be completely wrong by a factor of a few on the position of the planet that you're looking for. I'm not discussing the math here. So basically what this all means is that you need a more accurate dust models, and you need images to actually confirm where the dust is located. So let's do a little bit of a theory of light scattering and absorption by dust grains. This is my star. This is my grain. This is the photons which are arriving on my grain. And some of these photons are scattered in some direction here. And you define different quantities. One of them is Q-scar, the scattering efficiency, which is unitless, which is basically the amount of light, total amount of light which is scattered by the dust particles. You define another one that you just saw a couple of slides ago, which is the absorption efficiency, which is the amount of light which is absorbed by the grain, which means this is the amount of light which, amount of energy, electromagnetic energy, that will be transformed into thermal energy. So this is the energy that will be used to heat your grains that will emit at long wavelengths. You define the extinction efficiency. It's a little bit cut here, doesn't matter, which is the sum of the two. And you define the albedo that you heard about before, which is the ratio between the scattering efficiency and the extinction efficiency. Right. So you can calculate these quantities for any kind of grain. Some codes do exist to do that, but it's very complicated, especially if your grains have very complicated shapes. And it requires a lot of CPU time. So this is not necessarily the method that you want to employ to calculate these quantities. Fortunately, for spherical grains, you have the Mie theory after Gustav Mie. It's actually a very old theory, as you can see here. And what it does solve the Maxwell equation at the grain surface. And you end up with a series of equations that you can solve reasonably easily numerically. So you do that. And let me show how it looks like. This is the absorption efficiency as a function of the wavelengths. It's unitless again. This is the Blackbody absorption efficiency put here as a reference. And this is what you get for silicate grain, 10 micron in size, calculated with the Mie theory. You see what I showed before, namely that at short wavelengths, it absorbs and emits almost like a Blackbody, but at some point it drops, the efficiency drops strongly. And this break here in the QAPS curve is not occurring just by chance at this wavelength. It occurs where the size parameter, which is the ratio between 2p A is the grain size divided by lambda, wavelengths, is about 1. So for 10 micron sized grain, 2pa is about 60, more or less, and this is where at which wavelengths this break is occurring. If you take larger grains, you just shift this peak by a factor of 10 for 10 micron sized grains. And you see some diffraction pattern here appearing. Don't forget you deal with spherical grains. But basically, it essentially behaves like a Blackbody grain up to very large wavelengths. So you do expect the temperature of these grains to be very close to the temperature of Blackbodies. If you go to smaller grains, 1 micron sized grains, and you do see some features appearing here, because these are silicates, and silicates do have solid state features at 10 micron and 20 micron, so you see them appearing because they are small enough. And the same occurs for the 0.1 micron size grains. So let's see how it affects the calculation of the temperature of your grain. So you have the SED here of this particular example. In this particular example, the Blackbody temperature is about 60, so it's reported on this graph. This is temperature as a function of the distance from the star in AU. 60 AU is here. This is a formula. This is the Blackbody grain temperature that is predicted by the previous formula. Okay, so for 0.1 micron size grains, this is the curve that you get. So you see that it is hotter than the Blackbody grains because these very tiny grains do not emit very efficiently at long wavelengths. This is for 10 micron, 1 micron. This is for 10. And this is for 100 micron size grains. And you see it is more or less matching the Blackbody temperature. But what you see appearing here is mostly a degeneracy that Debbie mentioned earlier, is that for the same temperature, you can consider different grain sizes at different distances, which will produce exactly the same Blackbody temperature. So there is a degeneracy basically between the grain size and the location at which you put this population of dust particles. And this is where imaging is going to be very useful. Okay, so let's try to model real disks now. Again, this SED. So let's consider a very simple disk model, the simplest you can imagine. You assume you have a belt of dust, which is located at one particular distance, R peak. You assume that the grains, your belt of dust has a size distribution with one parameter, which is the minimum grain size of your size distribution, and you get the mass as well as a free parameter, but it's just a scaling factor. Then you can represent, you can get this kind of map, which is a chi-square map, as a function of the position of the belt and the minimum grain size of your size distribution. So blue is a poor fit, and yellow or white is a good fit. And you see immediately that there is a degeneracy. A small difference in grain size has a strong impact on the location of your belt inferred from the SED here. So this is a degeneracy if you fit the SED only. Fortunately, for this particular disk, you have images. And this is an Herschel image. You see the disk, which has an elongated structure here. And this is the PSF for comparison. It's not a great image of a disk, but this is enough, actually, to constrain the disk properties. So if you fit now the image with the same model, you get this. Obviously, you constrain the dust location, because this is an image, but you don't get any information on the grain properties, grain size in particular. So it's very obvious now that you want to combine both the SED, the PAX image here at 70 microns that I showed before. There was some other images at 100 micron and 160. And if you combine everything, then you get a location here, which tells you that your grain are located at this particular distance R and have this particular minimum grain size. This is how it works, and why you can use images to break the degeneracy in your modeling approach of the disks. So let's now improve a little bit the model. A more realistic model should take various things into account. The disk geometry. So you can assume analytical profiles, but you can also use such images, for instance, and say, okay, my dust is located here, there is no depth, it's here, so you can plug this kind of information into your disk model and try to fit the SED. This is what we're going to do very soon. You need to make some assumption about your grain size distribution, usually power laws, but it can also come from collisional models. You need realistic grain optical properties. I showed you that the mix theory is one good example to calculate the grain optical properties. And importantly, you need real grain composition. The mix theory needs optical indexes to calculate the efficiencies, absorption and scattering efficiencies, which means that you need optical indexes over a broad range of wavelengths from the UV to the millimeter because your grains are very efficient to absorb light in the UV and in the visible, but they do emit at long wavelengths. So you need the optical indexes for your grains to be available over this broad spectral range. And if you want to consider mixtures of different materials, then you need to find a way to do that. And the way to do that, an easy way to do that, is to use an effective medium theory, EMT. These are the two most famous effective medium theory, Maxwell-Garnett and Brueggemann, that actually are mixing the optical properties of different materials to produce an equivalent optical index for your mixture, and you plug this equivalent optical index into your mix theory to calculate the optical properties. All right, and then you need to do the radiative transfer in itself. Fortunately, your disk is optically thin, so that's reasonably easy. And from that, you get images, SEDs, and interferometric observables like visibilities on L. And then, this is not the least point actually. You need a strategy to find a good fit and to estimate uncertainties. You can consider different possibilities, simulated annealing to find a minimum in your parameter space. You could also consider Bayesian analysis. So you calculate your different models on a grid of parameters, and then you calculate probabilities for your parameters and uncertainties. You could consider different techniques. And the one I will use here is Bayesian analysis to model this particular system with these particular properties. Let me show you. This is HD181327, which has been specially resolved with the HST. We know where is the dust, no doubt about that. And which means that we can use this image to constrain the disk geometry, which is not anymore a free parameter in this model. Then what you can do is constraining the dust properties, not only the grain size distribution, but also the composition of the grains. And this is the goal of this approach here. So we run a grid of models, more than 1 million of models for different size distribution, grain composition, and we have been trying to fit the SEDs that you see here, and everything is published in this paper. And see if the first author is actually in the audience here, if you want to discuss with him. So let's do that. So the geometry again is fixed. We fit the SED only. We consider the simplest dust material, silicates, or maybe a mixture of silicates and carbon. And you see that it results in rather poor fits to the SED with very large chi-squares. If you consider different mixtures, still simple, silicates with some water, amorphous water ice, crystalline water ice, the chi-square does not really improve significantly. So you need to make your dust model more complicated to actually get a good fit to the SED. Let's first consider porosity before going to something more complicated. It helps a little bit to improve the fit in the far infrared, but not in the millimeter or submillimeter. So what you want to do is to combine everything together, silicates, carbon, water ice, and make your grain very porous. And once you reach that point, you can get a very good fit to the SED and calculate the ratio between the different composition, different mixtures that you put into your grain. So what do you learn from that? You learn from that that your grains are icy, very porous, and it recalls the dust properties that people are actually finding in the solar system, especially the cometary dust grains in our solar system. So this is interesting. Another interesting aspect is that when you do the same exercise for different well-documented debris disks, you end up with similar compositions, not necessarily the same volume ratio between silicates, ice, etc. But you need such a complex dust model to actually fit the SED and the images. This is the case for Beta Pictoris, for HR4796, that one, and the few others which are mentioned here. What you may notice is that all these disks are very young, actually, which is probably a bias, because most of these models have been using scattered light images to constrain the location of the dust, and it's much easier to detect a disk in scattered light when it is massive, so rather young. But what is interesting is that these systems are young enough to probably still support ongoing terrestrial planet formation. And so this dust composition that we find for the dust particles, which may reflect the composition of the kilometer-sized bodies that you don't see, might be actually the composition of the big guys which are currently forming terrestrial planets in the systems. All right, something else that we get from this model is a size distribution. Here I call S the size. It was called A before. Doesn't really matter. So it's a power law here. It's minus 3.4. It's very close to the minus 3.5 value that you expect theoretically for a system in collisional equilibrium. But what is more interesting is to actually calculate the dust mass. And I want to mention that because I think it's important for you to realize that the geometric cross-section in such a case is the square of the size, grain size, integrated over the grain size distribution. So this is something, if the maximum grain size is large compared to the minimum grain size, the geometric cross-section is proportional to the minimum grain size to something. While the mass, this is the opposite, is proportional to the maximum grain size to 0.4 here, which means that you do observe when you are doing an observation, you are sensitive to the cross-section, obviously, so you are sensitive to the minimum grain size. But when you want to calculate the mass, you are sensitive to the maximum grain size that you do not constrain observationally. Which also means that a grain size mass, is something completely arbitrary in any papers that you may see, in principle, unless you use an arbitrary approach, which is here defined as any grains smaller than 1 millimeter being defined as the mass, as the dust mass for your system. So take care when you see masses in papers. It is important to know up to which maximum grain size it has been calculated if you want to compare this mass with the mass in another paper. Okay, how to go further? One thing is that you may believe that, okay, we understand everything about the grain composition of the debris disks. This is not necessarily true. So far, I've been mostly talking about thermal emission. Here, I'm talking a little bit more about scattered light. This is the fraction of the light which is scattered as a function of wavelengths for this particular system, HR4796, from the visible to the near-infrared. And you see that the disk is red in the sense that it is scattering more light at larger wavelengths than in the visible here. And these authors, Kohler et al., have been trying to reproduce this trend using exactly the same kind of compositions that I showed you before. And it is doing a good job, actually, to reproduce this red color of the disk in scattered light. But this is not enough, because other authors did find that other kind of composition made of organic material, toluenes, is also doing a very good job in reproducing the red color of the disk. So there are still some uncertainties here, although I'm not completely sure these grains would reproduce the SED of this disk, but still. Another aspect which I didn't mention until now is that scattered light the light is not scattered isotropically. It is scattered with some phase angle, scattering angle, which is called phi here. And the efficiency to scatter the light in one particular direction is described by a phase function, which is called f phi, which you can actually see as a probability to scatter a photon in a particular direction when you integrate over the 4 pi solid angle. And we define then a symmetry parameter that you showed before in Davis' talk, which is the G parameter, which is the mean value of the cosine of the scattering angle, again, averaged over the 4 pi solid angle. So when G equals 0, that means that there is isotropic scattering. When G is positive, there is forward scattering, and negative, it is backward scattering. So how to use that? Oh, no, just a few examples before. This is a phase function as a function of the scattering angle. When the grains are small compared to the wavelengths, it tends to be the phase functions tends to be almost isotropic. But when the grains are getting larger, then it tends to be more anisotropic. And you can remember, I don't describe that. Okay, so that means that for the rate curve, for the small grains, you have a G value which is close to 0. And when the grains are big compared to the wavelengths, then you have a G parameter which is close to 1. So how to use that? Let's take again HR4796. The fit to the SED is pretty clear. You need micron-sized grains to fit the SED properly. And if you do that, you have a size parameter, the ratio between the grain size 2pi is the grain 2p the grain size divided by lambda, which is larger than 1, which means that the asymmetry parameter should be, especially in the optical and near infrared, the G parameter should be large. So you do expect a strong asymmetry in your scattered light image if you see if your emission, if your scattered light was dominated by micron-sized dust grains. This is a prediction in this paper of what you should actually see, and obviously this is not what you have on such an image. The observations tells you that the asymmetry parameter is rather small, less than 0.2, which, according to me, means that there is a problem with the Mies theory, especially to reproduce the scattering behavior of your grains, especially the phase function. This is not the only example. If you take the systems that we modeled before, the SCD, with some complex dust grains, HD1, H1, 327, we have exactly the same problem. The asymmetry parameter is rather small, but still you need big grains. So there is a contradiction between what you observe in scattered light and what the type of grains that you need to actually reproduce the SCD. But the thing is getting even worse. You had two papers last week in AstroPH, one by Perrin et al. And another one by Midi et al., observing, again, HR4796. You do expect for a broad range of grain sizes and dust properties that the light in total intensity and in polarization should be much higher at small scattering angles. So you would expect that your total intensity image and your polarized intensity image should have some asymmetry on the same side. And this is not what is being observed. In total intensity, you may convince yourself that it is slightly brighter on that side, I think by a factor of 2 or something. And obviously, on the polarized intensity image, it is much brighter on the other side. Okay, that's a mess. So one possibility to explain that, and this is what Perrin et al. have been proposing, is that the disk is perhaps marginally optically thick, and maybe it works, so it has to be explored. I think the GPI team is working on that currently. Another possibility is, again, that we are actually facing the limits of the Mies theory to predict the optical properties of the grains. And this would be at least my favorite explanation, but I'm not sure. Okay, and basically because it's really hard to imagine that the grains are actually spherical. If you look at grains which have been collected in the solar system, they much better look like this, with probably multiple scattering inside the grain itself before actually it is scattered toward the Earth. So you could imagine that it is changing completely the shape of the scattering phase function, for instance. All right. So there is a lot of work to be done I think, on this side. Something I only mentioned very briefly to see that there is still quite some work to be done on the debris disks modeling, and to make some kind of introduction with the next talk. I've been mostly talking about the cold debris disks, but now I'd like to show you one slide on the hot and warm debris disks, or exostecal disk. They are also detected, not yet imaged, because it's yet too much complicated to image them. These disks are very close to the star, so very hot, so you cannot see them very easily popping up above the photosphere at long wavelengths. You need to search for them at short wavelengths, and it's very complicated because the star is very bright. So what people are currently doing is that they use near or mid-infrared interferometry to detect a tiny excess. I will not explain here how people are doing, but this is typically what is being measured, this kind of tiny excess with near-infrared interferometry. And this is almost it. You don't have anything else, almost, to infer the properties of your disk, unless you try to use upper limits, unless you use a radiative transfer code, like the one I showed you before, and try to make something anyway. And here is a fit that, okay, matches more or less this point, and is consistent with the upper limits. And you can say something with that. The first thing is that the grains needs to be very small, because the disk needs to be very hot. The peak of the emission needs to be in the infrared. if you make these tiny dust grains made of silicates only, what you will get is beautiful silicate features at 10 and 20 micron. And you would have seen them with Spitzer, and obviously we don't here. So the trick here is to make your grains carbon rich, mostly, which is really cool because actually carbon actually sublimates at higher temperatures than silicates, which means you can get them even closer to the star than silicate grains and make your system even hotter. Okay, and this has been done for various stars, famous guys, Vega, Tossetti, Formalaut. I refer to this paper if you want to know more about how it has been done and what kind of dust properties you can get out of that. Okay, I'm essentially done. So I hope you've been convinced that images are absolutely essential when you do disk modeling because it breaks the degeneracy between basically two broad families of parameters, a family which is due to the geometry and another one which is for the optical property or the grain properties. So when you get information about the geometry of your system, obviously you can infer the dust properties much better, in particular the composition. The dust optical properties are essential to model debris disks. So if you observe a debris disk and you get a nice ring which is at a distance which is 2 or 3 times the distance you were expecting because you predicted the distance with a blackbody, don't panic, that's normal. A real disk should be at much larger distance than anything that has been predicted with a blackbody. And my impression is that we are reaching the point where the mystery is the limitation. That's my own impression. And we need to go further to describe the dust property, and especially if you want to interpret the beautiful images that are currently being obtained with GPy and with Sphere. And I will finish here. I'll take any question you may have. Thank you. So models beyond the mystery, you want to. There is one model which is called, which is named DHS, or distribution of hollow spheres. It actually relies on the mystery. You just assume that your grains is, you just calculate the emission of a grains which is first compact, then you put some vacuum in it, but you keep the mass constant, and you average everything. And it has been shown by a team in Amsterdam that it mimics reasonably well the optical properties of more complex grains, but that still relies on the mystery, basically. And it has been shown in the case of HF4796 to produce slightly better fits to the observations in Milli's 2014 paper, but still it does not really explain the brightness asymmetry, the reversal of the brightness asymmetry that we see between total intensity and polarization. If you want to do the job properly, then you need to consider complex codes like a code that is using the DDA approach, discrete dipole approximation. So you just assume your grain is a sum of dipole, and you calculate the electromagnetic field that is coming out from this collection of dipoles. And there is another approach which is called T-matrix, which does basically the same job but using a different technique. So you can do that. I mean, technically you can do that. The problem is that you have to assume some specific shape for your grain. So you can actually assume some inclusions, and you let your grains growing randomly, and then you calculate the emission, and you make another one. But it's very hard to know exactly which collection of inclusions will be representative of real grains, and all of them will average actually in a real disk. So technically it's feasible, but it's really difficult to know exactly what should be the right approach.
So you're scattering phase.
Okay, the question is whether the degree of polarization is actually decreasing due to the multiple scattering into the complex grain, right?
Yeah, inside the grain.
Inside the grain. That's a good point. I have no clue. I have no guess about that. But I would expect that, indeed.
Because
Yeah.
you were indicating